Just realized the whole thing wasn't, the sound wasn't working. That is unfortunate. But now we're noticing that basically I went through the working through the problem, and I thought they meant that you could just go straight down as if they wanted the right node, but they meant like you can only see this way, so you can only see 3, right? So you can't see 2. So now I'm thinking, instead of doing what I did originally, I'm thinking if we do a binary level traversal or level order traversal, but take the last element. If we do that, we could potentially get the outcome that we're looking for. And so how can we know during a binary level during a binary tree level order traversal whether or not we have ended a level, right? Because we usually push 1 on, right? Visit the children. We push 1 on to the queue, right? Do the work we need to, right? Then push its children on. And so we need a way to tell when a level is finished. Or a level is complete, basically. And so maybe after the final element, so for example, if we push 1 on, we push 2 and 3 on. We do our work on 1. We push 1 on. We start with 1 in the queue, and then we push 2 and 3 onto the queue. The 2 and 3 are different levels than 1. So how is it that when we're done with 1, we know that we're done with this current level? And that's a case we can handle. We can kind of hand wave away, because we can always just pre-push the value into the nums array. But if we're speaking in this sense, if we have 2, we push their children on, right? We'd pull 2 off of the queue, push their children on, 1, 2, right? Right. Then we pull 3 off of the off of the queue, and push 1, 2. Then we know that the level, we'd be done here, but how do we know that we're at 3? Maybe it depends. How do you know when you're done with a particular level? Maybe if we start implementing it, we'll be able to see when we can tell. So what we'll do is we'll take this queue, right, and we'll start it with root, right, and we'll say while queue.length does not equal 0, right, and we would say cur, typically, right, to pull off the first element, we'd say cur equals queue.shift to take it off of the front. If we take it off of the front, we'd now have 1. And typically you would push cur q.push cur.left and cur.right. In this sense, the level that we are currently at if we start with root, we'd push 2 and 3 onto the queue, and so our queue would now have 2 and 3 in it, right? So we'd pull Q off of the queue, push the children onto it. Maybe we can know our level is done when we pull off the last element from our particular level. So if we start with last in level equaling root, right? We could have a last in level starts at root, right? And we'll say, okay, we pulled an element off of the queue. We'll say if cur equals last in level, right? Which it does. Cur does equal last in level. Now, if it does, then we could do nums dot push last in level dot val, right? And then we also push 2 and 3 onto the queue. Now you go to the next iteration, right? Where are we going to set last in level? Right, last in level, right? If right exists, then it should be the right side. Right, it should be 3. So maybe we can say now last in level would be equal to if cur dot right, then we'll set it to cur dot right. Otherwise, we'll set it to cur dot left. And then we'll push cur dot left and cur dot right. Okay, so we have the queue length is equal 0. No, right? We pull 1 off the queue. It's last level. We push 1 onto the array, which is perfect, right? Then we set last in level equal to 3 now. Right, we push 2 and 3 onto the queue. We go back to the top, we pull 2 off of the queue. Now we've pulled 2 off the queue. Right, we're going to say, does it equal last in level? It does not. And since it doesn't equal last in level, right, the new last in level should definitely not be cur. So we definitely don't want to change it here. So we probably want to do these at the same time, right? Once we push it, the number onto the array, the last in level, right? We know that when we're doing this, we are the last in the level. So for the last in the level, then the rightmost element should be the last in level right. So for 1, this would be 3. And then for 2, right, we'd push L and R onto the queue. Right, but we wouldn't push 2 into the nums array. Then we'd go to 3. And 3 would be the last in the level, and since it's the last in the level, we would push 3, right? Because you wouldn't be able to see 2. And then we'd say our last level would be equal to this 3, right, dot right. And then we're going to do process 4 and 5. You can't see it, but once you get to 4, once you get to this null, right? And so one thing to consider is that we probably only want to do any work at all if basically that cur exists. And so I think this should also, we have so this gives us a good start as well. Let's see if this makes sense. So there's an example where this doesn't exactly work, and it's where our input is 1, 2, 3, 4. We're given the root of a binary tree, so if our input 1, 2, 3, then okay, we'll have 1, 2, 3, 4. That's what this is 1, 3, 4. When we do it like this, for this example, we only get 1 and 3. So why is that? Well, if we work with cur, right, we would push 1, and then our last level would actually be 3. We'd handle 2, right? We push its children on. They're both null. We don't do any work for them. We push them on anyway. We go to 3. From here at 3, right, we check if cur. I see. Right, if cur is equal to last in level, which it is, And then we say our last in level now is going to be 4. Right, and so we keep pulling things off of the queue until we get to 4. And see, does 4 equal last in level? Well, it should. Or maybe we're misinterpreting the array. Maybe they're saying it's like this. It's 1, 2, 3, and then 4 would be this first child here. In which case, the last in level would have to propagate as we work through it rather than assuming. So in this current sense, we have 1 in the queue. We pull off 1 in the queue, while we'll have 2 and 3, right? And cur does equal last in level, which starts at root. We push 1 on, and we say last in level is either the cur.write or 2. Well, cur.write does exist, so we push 2 and 3 onto the queue. Next, we pull off 2, and we say does 2 equal last in level? It does not. It does not. We push on children, 4 and null. Then we go to 3. 3 does equal 3, so we push on we push on 3, but then we say that the last in level has to equal null, which doesn't quite make sense, right? And I think this is the case where last in level could have a different value, because in the queue the next value is actually 4, which would make that the last in level. So we can have a few different cases here. Let's say if cur, we say if not cur.write and not cur.left. If neither of them exist, right, then we want last in level to actually be equal to the next element that we were going to take off the front, and that would be q q sub 0 if it exists. Otherwise, it should get the value of left or right if it exists. That works. Let's see if this whole thing makes sense. Yeah, so I think there's something about our assumptions that aren't making any sense. We can only see right. So in the case where neither of these well, this would not be a valid binary tree as that otherwise. So we'll take one more example. We'll have 1, 2, 3, and then null and 4, and what I'm getting is 1 and 3, where what they really want is 4. So if we take none of 3's exist, which is why we get 3, and we say the next last in level is the first element in the queue, which would be null. What we really want to say is it's the next non-null element. If that's the case, what we can do is just make sure to only push values that exist. So we'll say if cur.left, right, then q.push cur.left. And we'll say if cur.write, then you can push cur.write. So we'll exclude non-null elements, and we can exclude the case here, well, where the node itself has to exist, because we'll only push it if it exists. So we end up saying 1, 3, 5, 6 instead of 1, 3, 6. The nodes here are 1, 2, 3, 5, 6. And what we printed was I think what we want is not the first element in the queue, but the last element in the queue. I think this should keep our original solution correct. And it should also make this one good. So this works. The way we went about it was just a bit haphazardly. I kind of wish I thought through it more. I tend to take a simple solution and then keep modifying it. And then at a certain point, you just kind of need more and more failure cases to get to the correct answer. Is that a method that makes sense? Binary tree right side view. I don't even know if that's in here. So we would be good there. We'll also take this one as well for another time. But let's see if there was a better way to do this. I think the time complexity of this algorithm is actually linear time, since we're just doing a level order traversal, and linear space as well on the call stack. Let me remove all the extra. Two ways to traverse the tree: DFS, depth first search, and BFS, breadth first search. Here is a small summary. So we have binary tree traversals, breadth first search, iterative with queue. Depth first search, post order, recursive, iterative with stack, Morse, iterative with stack. So there's a few different ways. BFS traverse is level by level, right? And DFS first goes to the leaves. Which approach to choose? I think we definitely want BFS here. The problem is to return a list of the last elements from all levels, so it's way more natural to implement BFS here. Time complexity is the same linear time for both DFS and breadth first search. One has to visit all nodes. Space complexity is actually the O of H for DFS and O of D for BFS, where H is the height of the tree and D is a tree diameter. Both result in linear space in the worst case scenarios: skewed tree for DFS and a complete tree for BFS. BFS wins for this problem, so let's use this opportunity to check out the 3 different BFS implementations with the queue. All 3 implementations use the queue in a standard way. Push through into the queue, pop out a node from the left, push the left child into the queue, then push the right child. BFS, push one to the queue, add first left child and then right child, adding at the end. Pop out from right, add first right child, then left child. DFS, we went all the way down to 2. Right, let me be at 2. 3 BFS approaches. Difference is how to find the end of the level, exactly the rightmost element. 2 queues, one for the previous level and one for the current. 1 queue with sentinel to mark the end of the level. 1 queue plus level size measurement. So BFS, 2 queues. Let's use 2 queues, one for the current level and one for the next. The idea is to pop the nodes one by one from the current level and push their children into the next level. Each time the current queue is empty, we have the right side element in hand. So our current level is 1, our next level is 2 and 3. So we have 1, we push 1, or we do what we need to with 1, We push 2 and 3 on to the next level. Then we have next level. So initiate the list of the right side view, right side, initiate 2 queues, one for the current level and one for the next level, add root into the next level queue. While next level queue is not empty, initiate the current level equals next level. Empty the next level. While current level queue is not empty, pop out a node from the current level queue, add first, left, and then right child. This is the last one, makes part of the right side, you add it to the right side, return right side. So what does this look like? If root is none, return empty, which is what we had. Next level equals root. Now while next level, which is our queue, is not empty, prepare for the next level. So cur level equals next level equals a new queue. And while the current level still has elements, then we want to pop it off the current level and add the childs. And as soon as the queue isn't empty, as soon as the current level is empty, we know that we're done with a level. It's finished. Its last element is the rightmost one. And so this one is clever. One queue with Sentinel. So I've seen the Sentinel version before. And use a Sentinel node to separate the levels. Typically one could use null as a Sentinel. The first step is to initiate the root plus null. So if root is none, and they do actually have a Sentinel for the first one. So they put root in with null as a Sentinel. And they'll say prev and cur equals cur equals root and q.pop left. So while cur, right, add child nodes in the queue, q.append cur.left. The current level is finished and prev is its rightmost element. Add a Sentinel to mark. We still need a way to keep track of prev. Add a Sentinel to mark the end of the next level. Interesting. That's a cool one. So I'm going to try this one next time. Queue with Sentinel. So that works. Let's try, given the root of a binary tree, return its maximum depth. I think we've done this. I think we've submitted. Oh, we've done this problem before. Very long time ago. But I think it can be solved with actually a secret trick I learned from the Copy Ninja about recurrence relations. We can actually solve this problem as the binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So for every subtree, we need to consider both its left, or for every node, we need to consider both its left and right subtrees. That being the case, we could define a smaller function called, or maybe could we use max depth itself? I believe we could, right? If our tree is empty, right? If not root, right? Then we can just return 0, right? But if it does exist, right? What we want to return is 1 plus the math.max of max depth root.left and max depth root.right. I wonder if this is too simple of an approach. So this makes sense. Recursion, tail recursion. And one might have noticed the above recursion solution is probably not the most optimal one in terms of space complexity. In the extreme case, the overhead of call stack might even lead to stack overflow. To address this issue, one can tweak the solution a bit to make it tail recursion, which is a specific form of recursion where the recursive call is the last action in the function. Benefit of having tail recursion is that for certain programming languages, C++, the compiler could optimize memory allocation of the call stack by reusing the same space for every recursive call rather than creating the space for each one. As a result, one could obtain the constant space complexity for the overhead of the recursive calls. Here's a SAM solution of the optimization of tail recursion is not supported by Python or Java. So the queue that contains the next nodes to visit looks like there's a few ways to do this, but I'm fine with this being the method. If you do it, you can do it iteratively with the stack as well. Because technically this is depth equals 0, current depth. If root is not null, right, then depth is the max of depth or current depth. And then we do stack.append current depth plus 1. Actually, so doing this iteratively is not simple. I actually think we solved lowest common ancestor of a binary tree already. Oh, maybe we haven't. I'm so certain we did though. That's strange. Maximum depth binary tree. So let's try this problem. It says given the root says given the root of a binary tree, return the vertical. So given the root of a binary tree, return the vertical order traversal of its values. That is interesting. From top to bottom, column by column. So if two nodes are in the same row and column, the order should be from left to right. So I assume that 3 and 15 might be in the same column, but they're not. They are, but in vertical sense they aren't. But 9 would be by itself, 3 and 15, 20, and then 7. So that is interesting. We have another example here. We have 4, 9, 3, 0, and 1 would be in the same location, same row. Then we'd have 8 and 7. Then 4, 9, 5, these would all be in the same direction, same location, 8, 2, and 7. And so it looks like what they would like us to return is this actual array of tuples. So if that's the case, maybe there's a different, that is interesting. So I'm getting the idea that we should use binary, we should use a level order traversal in some sense. And if we use a level order traversal, maybe it's possible that we could reconfigure it in a way that makes sense. So just to take this through and see if we can make this make sense, if we did level order traversal, we'd have 3, 9, 20, 15, 17, 15, and 7. And it seems like additionally, our goal is not that. Our goal is 9. Our goal is 9, 3 and 15, 20 and 7. So this is interesting. So I think this is what it would look like essentially in the arrays. I'm not really seeing a way that we could potentially rearrange this to do that. So maybe we could do a different version, maybe where we decide to find a new root of the binary tree. Maybe we could do a level order traversal on that. So let's just say, for the sake of the example, we could do a level order traversal on 7 if we were to rotate this entire graph. This graph rotated would now look like 7, 20. On 20 would have 2 children, would be 3 and 15, and then it would have 1 child, which would be 9. Now, is this closer to what we want? We'd have 9. Oh wait, this is much closer. We'd have 9, 3, and 15, and 20. So if we can do a binary tree level order traversal, maybe, well, basically a BFS on the rightmost node, maybe we can make this make sense. So let's see, if we were to look at 7 and we do a BFS here, we'd have 7, 8, and then 3, 0. Well, I don't know if these would all be in the same. Let me just redraw this tree to see if would they all be in the same location. We could put 8 here, and then 8 would have 2 children, 3 and 1. Children 9 would be 3 would be 9, and then it would have 4. And then 8 also has another child, which is 1. 9 has a child, which is 0. So 7 is, and then has a child 8. 8 has 2 children, 3 and 1. 3 has 9 as a child and 4. 9 has a child of 0 as well. And it doesn't exactly line up in this example, because if we did a level order traversal on this, we get 4, 0, 9, 3, 1, 7, 8, 3, 1. So, yeah, 3, 1. So maybe there's yeah, this is interesting. So it doesn't necessarily work in that sense. It does work for the smaller case here, but that must be a coincidence. So maybe another angle we can take this at. What if we visualize the binary? What if we look at it as more general? Maybe we look at it as a graph. Could we find what we're looking for in that sense? So if we're looking more in a graph sense, and we started at 3, we'd go to 9. There's no real order here, and we'd be at 20. Then we have 15 and 17, which doesn't exactly put anything into any particular groups, or maybe it could, right? Depending on the node you start at, right? If you have a node, right, we could have an array. This is an array of tuples, right? If you're in your current array, which would be 3, if you have a left node and a right node, then 9 goes in the left subarray next to you, and 20 goes in the right subarray right next to you. Then you would do the same for 9, nothing exists. But if you do the 20, right, 15 goes in the left subarray, and 27 goes in the right subarray. So that does make sense. Let's try it again. So for 3, you have this array of 3. 9 goes in the left subarray, 8 goes in the right subarray, right? And then for those children, you're 9, well, 9 goes in the left, 0 goes in the right, which is going to be good. At 8, you'd have 8 goes in the, you'd have 1 goes in your, so when you go to children, it's a little bit more confusing. So you have a subarray, you go left and you go right. But what exactly gives you an index? Maybe we could pass the index, right? Maybe we'll start somewhere that makes sense, like 0, or somewhere in the middle, like it might even be something easier, like that's not an array, that's more of like a linked list of arrays potentially. And so what you could do is you could say iterate downwards, and you'd have a reference to the subarray to the left of you and to the right of you. And you would say, okay, well, 1 goes in the one. Oh, I guess each node gets its own subarray. So yeah, each node gets its own subarray. So 3 would get its own subarray. I see. Each node gets its own subarray unless it exists already for another node, but that's kind of the issue. Subarray, left subarray. So I think if we could if each node, wouldn't have us, or would be given access to subarrays L each node would be given access to subarrays L and R. And so to start, then we could say that we start at root with the target node, which would be 3, and we'd start it with, so definitely be done recursively, and we'd give it access to nodes L and R, right? And we pretty much do a depth first search, and the node or the array that you would have access to would be relative to what you've been given to start. The depth first search I'm thinking for here so the depth first search that I'm thinking here maybe may not be depth first, may not be the best idea, as we go far left, right? Actually, maybe it could work if we do something like NLR, right? You process your node, right? Create your subarray, then you'd go left, right? Process your node. Where do you belong? You create a new subarray, right? And then you'd go left. If you go left, right, then your new L and R subarrays, you can only give someone a right subarray. And at the end, maybe we can concatenate them all. So I think maybe this could work. So you'd go left, right? You'd have access to your left subarray, right? And your right subarray, right? And 4, right, would have its own subarray. You'd go right, and you'd have access to your left subarray, which would be your parent, basically. So it'd either be, actually no, because it's hard to tell. So this wouldn't exactly work. So there has to be a way we can visualize this as a graph to some degree. Maybe not as a graph, but we can rotate it. Or if we start at a different node. Hmm. Three, 9, 20, 15, and 7. 9, 20, 15, and 7. So what if we revisualize it? And what do the vertical nodes have in common such that they create a different image? Maybe what we could do is visualize the entire array as a matrix, right? Where the number of the total size of the matrix, right, would have to be equal to, or 3 nodes high, right? So we'd have 3 cubes. So 1, 2, 3, 1, 2, 3, 1, 2, 3. It's a little tough since viewing it as a matrix, there are still portions where they would overlap, so that doesn't quite make sense. If we do level order traversal, I think there's really something there with the level order traversal. It really worked the first time, but it's because this subtree was very simple. What was the requirement that this was filling? These would still match up. So let's try and recreate that tree and just to see if we were off slightly. We have 7, right? And its child would be 8. 8 has 2 children, 3 and 1, right? 3 has, yeah, where does 0 go? I think I did misrepresent. We have 9, right? And 9 has 2 children, 4 and 0. Now, if you were to do a binary, if you were to do level order traversal starting from 7, then it's actually not correct. Maybe the goal is to split it in half. What if we split it in half? So this 7 entire tree, what if it became 7, 8 as a child, and we have 3 and 1, and then we would have the left subtree, which would be 4, right? And it would be 4, and we'd have 9 as our child, and we would have 0 and 3. Now, does this actually give us the answer that we want? 7 and 4 would have to be separate on each end. 8 and 9 would be separate on each end. But for some reason, this together, this part right here, they should be fused. It's unclear why that is. we view this one, which nodes have access to 5 and 2? Do both 0 and 1 have nodes 5 and 2? I think that might be what they're trying to explain. If you look at this one that way, you can just give 0 and 1 to more nodes each. This would be 5, 2, and this would be 5, 2. The output, if we do a level order search here, level order traversal here is 5, 2. 5, 2 isn't even included as potential output here. Oh no, we have 5, 2. We'd have 3, 1, 0, 3. Oh, our numbers are completely different. Our numbers are completely different. You'd have 4, 9. The 2 children would be 3 and 0. And then 0 would have children's 5 and 2. Then we'd have 7, 8. And then we'd have children 3 and 1, both of which have 5 and 2 as children. So the output would be 5, 2, right? Then we'd have 3, 0, 1 as a potential output, which we do here. Then we'd have 9 and 8, and then 4 and 7. So maybe the levels, right, for the left, the levels for the left and right subtree should be inserted into their respective arrays based on the offset of their direction. So if we had an array, right, how many arrays are we going to have? Maybe it's going to be 1, 2, 3. Well, 1, 2, 3. Maybe it could be height plus 2 arrays. Let's check up here. We have 1, 2, right? We end up with height plus 2 arrays. 1, 2, we end up with 1, 2, we end up with 4 arrays. So total R's equal height plus 2, right? If we do a binary level traversal, right, for the left subarray, starting from 4, interesting. Maybe we're just really visiting the neighbors. And it really depends on how far away from you or how many nodes away you are from where you started. That is what really says how far you are or what level you're in. So we go 1 node away to 9. This is saying that this should be at level 1. Level 1 just means for the left subtree it should be at index 0 plus 1, which it is. Then we go 2 nodes away, which means it should be at index 0 plus 2, which is here, and 0 should be here, which is at index 0 plus 2. And then if we do the same for 7, right, we'll travel 1 node away, which means that we should be at the end of the array, right, last element in the array, minus 1, which would be 8. You go 2 away, it would be the length of the array minus distance away, which is 2. And then this would also be 2 because it's 2 distance away from where we start. But the only problem being that when we do visit 2 here, this is technically 3 away. So it'd be the end of the array minus 3, which is 5 minus 3 is 0, 1, 2, which would put us in the center. Oh, no. It'd be 1, 2, 3, 4. All right, it'd be the end of the array minus 4, which would be index 1, which puts us right here, and the end of the array minus 4 as well. This would be 1, 2, 3. So with this 2 here, I actually don't know where it goes. I think I see what's happening though. If we visualize a tree here like this, 7, 8, right? If we ever go right, it means we add 1, right? We add 1, right? If we go right again, we add 1, which means it should be 2 away from the center, from the end, which would be right. Then if we go right again, which would be to 2, we should add 1 more. Well, no, this is 2, so we have 5. So it looks like we're almost there. So there are some smaller things. We'd have 5 and 2. We have 9, 3, 0, 5, and 2. So we have 5 and 2. I thought if we went distance away, then we could know. And they both actually reference the same nodes. So I think I see a new way. I was trying to keep the tree the same way as it is and reuse it. But what if we changed it completely? What if we modified it? If we had 7, right? Let's just say 7, 8 and 2 are direct children of 8 and 2 are direct children of 7. If that was the case, if 8 and 2 are direct children of 7, then they would actually be perfectly in this level order traversal. And the same thing for this, if 5 and 9 were children of 4, then you can just do a level order traversal. So I think what really matters is finding a way to get the rightmost node and connecting it to the leaf. Rightmost node and connecting it to the leftmost remaining leaf. A rightmost remaining leaf. And if there doesn't exist one, then we're probably fine, right? Because we don't want 1 to be our rightmost least. But this technically would be our rightmost leaf. Our rightmost leaf which cannot share the parent of 7. So we need our rightmost leaf, right? And then we need our rightmost leaf that doesn't share parent of RML. And if we do that, then we can say RML.right equals new rightmost leaf, right? From there, we'd still have to rotate the entire tree somehow. So you have to rotate the entire tree somehow, and or reframe the tree. If there's a way we can use it the way it is, what if we get the output as it is, right? If we did level order traversal as it is, R0, we'd have 3, 98, right? 4, 0, 1, 7, 5, and 2. And the two nodes that we're actually interested in are going to be in the node's length, the list length divided by 2, floor, which is going to be here. And then in here, we want to take the first and last nodes, right? 4, 4, and 7. So if the last nodes 4 and 7, right, how can we do an iteration? How can we do an iteration through that would give us the order that we need? It looks like we want to go from 7. We're going to go from 7 to 8. And then from 8 to 3. And then from 3 to 9. So that doesn't necessarily add up. So I don't think that makes sense. That's the case. So this doesn't necessarily make sense. Vertical order. Maybe what if we started from a completely different angle? What if we went to it looks like this problem has a lot to do with what if we went to the bottommost leaves that we could, 5 and 2? Does that help us make this make sense? Level order would just be the same thing, but in reverse, you had 4, 0, and 7. We can get 4, 0, 1, 7. I think there's definitely something here about doing the first level order traversal to get 4 and 7. And then if you could do a level order traversal there, what if we visualize this as a new graph and we'll take distance away? So it's 2 distance away. And then if we go here, it's still 2 distance away, so it's the same. The problem is when you have it continuing. 1 distance away, 1 distance away, 2 distance away, 2 distance away still. Is this still 3 distance away? So the thing is, we'd be at 1, and we don't want, just here when they both share the same nodes. So we're at 1, we could go right. I guess if how many rights you make, how about this? If you just went right, wait a second, we'd have 7, 8, 3, 1, and then 5, 2. So if you have 2, 5, 2, if you go right, you would place 2, one more, you'd place 2, but you want it to be on the complete other side. That would be the last element in the deepest element in the tree. And if you did it for the other side, you'd have 4, 9, 3, you'd have 0, 5, and 2. So the similar question is binary tree level order traversal. It definitely has something to do with this. But what if we converted the tree to a graph? And it seems like the solution works until you get to this point. Maybe if we can confirm that we can't iterate through both at the same time. Maybe we confirm that they both have the same children, then we should skip it. We have 3, 98, 4, 0, 1, 7, 5, and 2. Binary tree level order traversal, practical use. Let's just say we kept it regular binary tree order traversal. We have 3, 9, 8, 3, 9, 20, 15, 7, 3, 9, 20, 15, 7. Again, if you could connect these two and then do a binary tree level order traversal, they would line up together. Maybe the same thing here. Even if you just start from one side, 7, 8, 2. Level order traversal. Even though 0 and 1 aren't necessarily connected here, what if we did connect them? What if the first step you could do is go through and join any nodes that have 2 of the same children as references? Then this would be one tree. Then you could do level order traversal. You have 3, 0, 1, 9, 5, and 4. But you need to basically. So how could you reverse this? If you were iterating, you got to the rightmost leaf, you had access to the previous node you got to, you'd say the current node dot left equals parent. What if this is more of a post order iteration where you do like LRN, and you could do LRN to maybe keep track of all of the nodes you're visiting. You'd have 7, right? So you did LRN or RLN. So at 3, right, you'd go R, right? And at 8, you'd go R, right? And at 7, you'd go R. You can't go L, so you'd go N. And so you'd say, if you could keep track of it, you'd say this current node's right, and this current node's left node would equal our parent, and the current node's right node would equal the node that we visited 2 nodes ago. So maybe we always have access to our node history, at least 3 nodes. So let's imagine that we have 3, right? You'd go right, you'd push 3 onto it, right? Then you'd push 8. Then you'd go right, you push 8, you'd go right. And then that's why R and L, so in order is not going to work. So if you did RL, you go right, you go to 8, right? You go right. Both 3 and 8 are on the queue. They're on the stack. Both 3 and 8. You go R. Then you go R. Then you go here. You go R. Can't go left, so you get N. You have access to 3 and 8. But this is not what you want, because you want access to 7. You want access to 7 and 8 and 2. So what if we used a hash table? What if we used a hash table of some sort? What if we used a hash table of some sort to keep track of the parents? If we had track of the parent, then we could have a nearby node. we could visit 3, 1, and 7. I think we need assistance on this one. So yet another problem about binary tree traversals. One would probably know the common strategies to traverse a tree data structure, BFS and DFS. DFS strategy can be further distinguished purely in post order. One is not familiar with the concepts of BFS and DFS. One can find the corresponding problem in LeetCode to practice with. Also, we have an explorer called Q and Stack, where we cover both BFS and DFS. So we're in the vertical order of a binary tree, which actually implies 2 suborders where each node would have a 2-dimensional index denoted as column row. If you look at a binary tree horizontally, each node can be aligned to a specific column based on its relative offset to the root node of the tree. Let us assume that the root node has a column index of 0, then its left child would have a column index of -1, its right child would have a column index of +1, and so on. Row-wise order, now if we put nodes into a vertical dimension, each node would be assigned to a specific row based on its level distance to the root node. Let us assume that the root node has a row index of 0. Then both of its child nodes would have the row index 1. Above definitions, we can now formulate the problem as a task to order the nodes based on the 2-dimensional coordinates that we defined above. These nodes should be ordered by column first, then further the nodes on the same column should be ordered vertically based on their row indices. So the row is based on the distance from the root, whereas the column is based on the offset of going -1 or right 1. So going right would be going 1, going left would be going -1. That being said, can we solve it with the hint? We basically visualize it as a matrix we said earlier, except we would have 0 to start, right? Our root node, which would be 3, right, would actually start up here, and the column, the column would actually represent 0 here. And if you go left, you have -1. If you go left again, you'd have -2. And then this would be a row of 0. Interesting. And then we can have 9, which would be actually fit into this row, and then 20, which actually fits into 1 and 2. Then you have 15, which actually fits back into 0. And then you would have 2, which actually fits, 7, which actually fits into 2. And the output that we would return would actually be the column order. So it'd be 9, 3, 15, 20, and 7. 9, 3, 15, 20, and 7. Interesting. And so what we could do is just order all of the nodes by, eventually we would have a list of column IDX, which is really just a function of going left or right. An array of tuples of column IDX to actual value. So when we say it like that, we could define a recursive function. Helper should be root, which would, you could actually return, actually no, we wouldn't return it, but we'd call it column wise, and we'll pass in the root and our start, which would actually be 0, and our helper function take a node, which is a tree node, and it would return, would it return anything? We wanted to return this array of tuples. Maybe that's easier done by passing in tuples to be an array of arrays. And so what we'd pass to start would be an empty array, then 0, which would be our current index. From here, what kind of iteration could we do? Depth first search actually sounds the easiest here, since we just have to keep track of if we're going left or right. So if the node doesn't exist, then we actually just want to return. We're actually not going to do anything. And so the value we're modifying out here, tuples is an empty array. We're actually not going to return anything. And then from here, 3 does exist, right? So we actually want to do tuples dot push. This tuple is going to be IDX and the node dot val. And then from here, tuples dot push IDX node dot val. And then from here, we just want to do helper node dot left with IDX -1 with tuples. Do the same IDX plus right for tuples. And then here we'll have our column-wise ordering, an array of column-wise values. We would have something like this. We'd have -1, 9, 0 would have we'd have -1, 9, and then we'd have 0, 3, 0, 15. And we'd have 1, 20, and then 2, 7. And if that's the case, maybe we could make this even better. By instead of passing in tuples, we could pass in a map. This map could be of type number to number. To type number array. And so here we could have a new map of type number to number. Then we'll change both of these calls from tuples to map. Instead of doing tuples.push, what we'll do is say r equals if map.get idx has an array, or if map.has already has an array for this index, we want to get that value. Otherwise, the array that we want to set it to is just going to be this array with no.val in it. Say map.set idx equal to this array. And so if we do console.log map, you might have to return something for the type error. Oh, this needs to be a number array, and we can return this back to the way it was. So our map is perfect. So we have 0, right? Which maps? No, 0. Oh yeah. So we have 3, right? We should have 9 and 20 both mapping. Level. I mean, the vertical should be of 9, 3, and 15 together. 20 and 7. So we have 0 at index 0, which is 3. And then we have 9 at -1, and then 20 at 1, which makes sense. But we don't have 15 or 17 at all. Or 15, yeah, 15 is not in the map at all. Could be our map, could be the way we get the, oh, map.get, right, idx. So we'll actually set it to an empty array, and we'll say r.push node.val. So now, right, at the 0th index, we actually do, right, if we visualize it, we do actually have 3 and 15 together. And so we do have our goal arrays, which is 9, 3, 15, 20, and 7. And we can actually just return do map. We just print map.values iterator, and I think we can just do array.from. So we'll say return array.from map.values. Output was 315. So maybe they're looking for it in a very particular order. If two nodes are in the same row and column, the order should be from left to right. Row and column order should be from left to right. So 315 I guess in that sense, if they want it in the order of 9, 3, 15, 20, and 7, we're giving them 3, 15. That's the case, maybe we do something like this, where we do L first and then R. So our output is in the incorrect order. We actually have 0, 3, 1, not 3, 0, 1. If you're going L and R, L, 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 N, R, L, and R, and then N. So by the time you would have 0, then 3, and then 1. They want 3, 0, 1. So I think what they really want is LRN. This example, we're putting it in incorrect order. They want 3, 0, 1. So doing L and R, we also didn't dedupe values. So in this case, where two nodes are connected to the same value, but we still get 0, 3, 1, because we would get to 0 first, then 3, then 1. So maybe what we want to do is instead keep doing what we're doing, but do level order instead. We'd level order push the left node on with the new index, the right node on with the new index, left node on with the new index, right node on with the new index. Then 9 and 8, then 4 and 7, then 5 would go where 9 is right after 9. 0 would go first, and 1 would come after, and then we have 5 and 2. So definitely have to do this with breadth first search to get the correct order. So we have to kind of reduplicate what's happening here. Redo it. We'll say we'll use a queue, which is going to start with root in it, and we'll say while queue.length does not equal 0, but the queue is going to have a root and a node to start and a depth. Depth is going to be 0, and we're going to say const cur depth equals queue.shift. Give the cur and the depth. And we're still going to want that map from earlier. Say const map equals new map. We'll still use number to number array. Say const r is equal to if map dot has depth, right? Then get that array for that depth. Otherwise, give me an empty array, and then we'll do r dot push cur dot val map dot set cur dot val or the depth. which is going to change depending on the direction you're going. It's going to be, you're going to set the depth equal to this array, right? And then instead of just pushing it onto the queue like I usually would, you would do queue, and we're going to skip any null values. We'll say if cur.write queue dot push the tuple of cur.write depth plus 1. So when you're going right, you're going to add 1, and when you're going left, you're going to subtract 1. And then we'll do what we did before. We'll do array dot from map dot values. We r dot push cur dot val. We have to push something onto the queue if it exists. Line 31. Tree number or tree node is not assignable to parameter of type number. Argument of type number or tree node is not assignable to parameter of type number. So we could just do is say tuple equals q dot shift depth equals tuple sub 1 cur equals tuple sub 0. Type tree node is not assignable to type number. Line 34, type val does not exist. Val does not exist on type number. Basically need so we do get 3, 15, 29, and 7. The order they wanted it in was 9, 3, 15, 20, and 7. So we're still in the incorrect order. Doing a depth first search earlier. Actually, I think what we want to do, what we did earlier was fine. We just want to order it. I think what's most important is with this example, we actually get 301. Then the ordering problem can be fixed by the key index. This one we actually get 310. Probably because we want to do something like this. Now if we get 301, we can sort the, it's perfect, so we can sort, say, So we can do map. We spread the map into an array, and we can sort it by the keys and the values by the key, and we'll say a sub 0. This will be in ascending order. A sub 0 is less than b sub 0. So we'd have the map, we'd sort it by the keys. Since we're sorting it by the keys, have it in ascending order, sorted, so we can actually print okay, this is actually the ideal outcome. We have 4, 9, 3, 0, 1, 8, 7. And then all we'd have to do is return sorted.map tuple, and what we would want to return is tuple sub 1. push cur.val. So it's possible that if not root, right, we want to return an empty array. Okay, so this works. The columnized order, I wonder how they do it without. The foundation of the problem in the review section. The most intuitive solution inside of the problem would be applying the Vfs traversal. Nodes will be visited level by level. Vfs traversal, we naturally can guarantee the vertical order of the visits. The nodes at higher levels, large row values, will get visited later than the ones at lower values. However, we're still missing the horizontal order, the column order. To ensure this order, we can do something additional processing during the Vfs traversal. Is that we keep a hash table as key to value, where we keep the node values grouped by the column index. The key in the hash table would be the column index. Corresponding value would be a list which contains the values of all the nodes that share the same column index. In addition, the values in the corresponding list should be ordered by their row indices, which would be guaranteed by the Vfs traversal, as we mentioned before. We elaborate on the steps. First, we create a hash table named column table, which we did. So the Vfs traversal common code pattern would be to use a queue data structure to keep track of the order we need to visit nodes. Initialize the queue by putting the root node along with its column index value of 0. Then run the Vfs traversal with a loop consuming elements from the queue. Each iteration within the Vfs would pop out an element from the queue. Element consists of a node and its corresponding column index. If the node is not empty, then populate the column table with the value of the node. Subsequently, we then put its child nodes along with their respective column indices, column -1 and q. Yeah, we shouldn't have used depth. We should have called it column. At the end of the Vfs traversal, we obtain a hash table that contains the desired node values grouped by their column indices, which the values they are further ordered by their row indices. Then sort the hash table by its keys. Column index in ascending order, and finally we return the results column by column. This is almost exactly our output. And also sorted by the keys. Time complex would be n log n, n is the number of nodes in the tree. In the first part of the algorithm, we do BFS, which is linear time. But to return the order results, we have to sort it by n log n. So the overall time complex would be n log n. Space would be n because of the queue. two of the nodes with the same comment. Hash table consists of keys and values. In any case, values will consume linear memory. Values can vary. In the worst case, each node has a unique column index. There will be as many keys as values. During the Vfs traversal, we use the queue date structure to keep track of the next node's visit. At any given moment, the queue would hold no more than 2 levels of nodes. Binary tree, the maximum number of nodes at a level would be n plus 1 over 2. There's also the number of leaves in a full binary tree. As a result, in the worst case, our queue would contain n plus 1 over 2 times 2 equals linear space. Basically a reordered hash table of that as it just goes forward. So overall space complexity would be your time.